Before everything goes completely sideways on us, I want to think about some experiments a person could do. You could set up a lab somewhere, elaborately indicated by these two walls that I've drawn in. You could have a table. On the table, you could have a source of electromagnetic radiation. These are waves in both electric and magnetic fields. What you could do is you could measure the time that passes between successive crests of the electric field, say, and adjust your radiation source so that the time between these two crests is 1 second. In essence, you could use the frequency of the electromagnetic waves as a clock. Imagine you have an inertial reference frame. Initially, two individuals, Fred and Jane, are at rest with respect to this inertial reference frame. At time t equals 0 as measured by the frame, they both fire rocket engines and begin accelerating to the right at the same rate as measured by the reference frame. I'm not going to prove this, but it's not a hard calculation. They are neither getting closer together nor getting further apart. Also, at the moment that they begin to press the acceleration button, Jane emits a photon traveling towards Fred. Jane, who was at rest with respect to O at that point, will say that the energy is Planck's constant times the frequency F, and O will agree. Fred has no say in the matter yet because he's some distance away. O has individuals stationed at every point that we want to make a measurement at. As time progresses, both Fred and Jane accelerate to the right. The photon is traveling towards the left, towards Fred, and will eventually reach Fred. When Fred receives the photon, he is not at rest with respect to O anymore, though. Fred, having accelerated to the right, now has a speed to the right. This means that Fred is going to measure the energy of this photon as being more than h times f. Fred will see the photon as being blue shifted. At first glance, that doesn't seem so bad, but we're using the frequency of the light wave as clocks. That says Fred is going to say that Jane's clock is running faster than his. Of course, you could argue it the other way too. At t equals 0, Fred, having set up his own atomic clock, sends one of his photons towards Jane. If the acceleration were not happening, or even if Fred and Jane were moving at the same constant speed always, then Jane would receive the photon and say that its energy is the same as what Fred says it is. But that's not what's happening. As time passes, Fred and Jane are accelerating off to the right. The photon is traveling to the right. When it finally catches up with Jane, Jane is going to be moving faster than she was at the beginning. She was stationary at the beginning. Jane is going to say the energy of that photon is less than what Fred says it is. Jane is going to measure the energy of the photon as being redshifted, which, thinking about the atomic clocks again, that means Jane is going to say that Fred's clock is running slower than hers. This is very peculiar. You've got two individuals. They're not getting closer to each other. They're not getting further away from each other, but their clocks are running at different rates. One of the more humorous ideas that our flat Earth friends have is that gravity isn't real. Some of them will actually tell you that the Earth is flat and is being accelerated upwards at 9.8 meters per second squared, presumably by some gigantic rocket engine or something. If this were true, which it isn't, people on the flat surface would experience what felt like gravity to them. So I can take the situation we were just talking about, imagine that this bizarre scenario is true, and say that Fred is actually in a model rocket ship that's glued to the side of a building, and Jane is glued to the side of the building up above him. Everything we talked about on the previous page is still on the table. This semi phony gravity seems to be making clocks run at different rates. Back in the early days of the space program, people often envisioned building giant space stations in the shape of a ring and then revolving them so that you would have kind of an artificial gravity. I want to think about this situation also. My ring is going to have radius r and angular velocity omega radians per second. The speed is omega times the radius, and the acceleration is omega squared times the radius. I'm going to imagine on the inside of my ring putting up a small building, a building of height h. At the base of the building, I'll station our friend Fred, and at the top of the building, Jane will be located. Also, I'm going to assume that the h is much less than the r, so anytime I have a quantity h divided by r, or something like that, I'll be able to neglect those terms. The speed of one of these people is omega times how far out from the center they are. Because of all the work we've done before, I can now write out the relationship between proper time for either one of these people as compared with the coordinate time of the inertial frame that we're using to do our measurements. And I'm momentarily going to drop back to using meter kilogram second units so that I get a good feel for the order of magnitude of these things. What I'm going to do is I'm going to take this formula and divide it by that formula. In this way, we can eliminate the parameter t and get a direct relationship between proper time as measured by Fred versus that measured by Jane. Simplifying the fractions, the change in proper time according to Fred divided by that according to Jane is this radical divided by this one. I choose to write the top of the fraction as the 1/2 power of 1 plus something. The rest of it is the negative 1/2 power of 1 plus the negative of something. I want to write it that way because if the something is small, as it is in this case, the binomial theorem from Calculus 2 tells me that 1 plus something raised to the k power is, to first order accuracy, 1 plus k times the something. So I'll use the binomial theorem to approximate each one of these two things and then multiply the results together. This quantity is very small, so is that one. So when I multiply them together, compared to other terms in the product, they are very small, so I'll neglect them. Simplifying the algebra, we see that the r squared terms inside the bracket cancels out. 2 times r times h will be much bigger than h times h. So we will ignore that. The only important thing inside the bracket is the minus 2 times r times h. Omega squared times r is this fictitious acceleration due to gravity, though, so I can write this in another form. If you take the acceleration to be 9.8 meters per second squared and the height of the building h to be 100 meters, this quantity works out to be something in the range of 10 to the minus 14 or thereabouts. This is in good agreement with the Pound-Rebka experiment of 1959. So after all of this talking, a person might be thinking, well, so what? Remember our friends, the inertial reference frames. Newton's first law must be true. The geometry must be Euclidean. The clocks must be synchronized. And the speed of light in a vacuum must be constant. That's what constitutes an inertial reference frame. What we've just found out is if you have a group of people, individuals, even if they're at rest with respect to each other, if they are accelerated with respect to some inertial frame, the group of people themselves do not constitute an inertial frame because their clocks don't say synchronized. We haven't talked about Newton's first law, but it fails too. It's going to turn out that the geometry is not Euclidean. The speed of light business is going to get awfully wiggly unless we're very careful about what we're talking about. So then you might say further, well, again, so what? Accelerated groups experience things that are very similar to gravity. It's not that big of a stretch then to think that gravity might mess up inertial reference frames, as the Pound-Rebka experiment shows that it does. If there's gravity around, then there is no such thing as an inertial reference frame. This is obviously bad news for us because every thought we've had has been connected to these inertial reference frames. All is not lost. It's going to turn out that we can do some calculus things in order to deal with this situation. We're going to have to sneak up on this in 2 steps. So far, we've been dealing with coordinate systems in which the coordinate axes were straight lines. We're going to have to give that up. And then secondly, we're going to have to deal with the situation where we explicitly do not assume that the geometry is Euclidean. That'll be the other big step. Once we've done that, we will be ready to start talking about what we're really interested in here. That's probably enough for one day. I'm going to stop here. I hope everybody has a good day. I'll talk to you again soon.